Well, let me just give you an update. All right, so I was going to go through section 5, 6. This is using something called a Jacobian. It's a determinant second derivative to get a relationship. If you have like random variables, call it theta and phi, and regardless of the distribution, but then you create new random variables like x and y, like we did with that problem, cosine of omega t plus phi, and that. And then if you have those and you want you say you sum them, you say z is equal to x plus y, and you want the probability density function for z, you can use the method talked about in section 5, 6, and it's advanced calculus that uses something called a Jacobian. However, it doesn't really buy you much. So I'm gonna, and I looked at Tom Denny's work and other people's work. They have omitted that too. I'm going to finish section 3-5 and then go into section at the same time 3-7. Now 7 uses what's called the characteristic function. I'm just going to use the Laplace transform to do it because you guys are familiar with that. It makes life easy. Now, with that in mind, before I start, any questions about anything so far?
So just omitting section 3-6.
Yeah. You'll know from the problems that I'm not going to. Jacobians are fine to do and stuff like this, but I looked at that and I did some of the problems. They're really not buying you anything in terms of an ability to solve things. It's still a pain in the butt to do all that. Any questions at all? Now, last time, what's the last problem we did? 5-3 or which one? All right, why don't we just do this? I'm going to start there. I'm going to go a bit quick, but how many took a look at this stuff? Just level with me. Okay, about half the class. I'm going to warn you about this, though. This is more complicated than anything we've done, and it gets more complicated in a hurry if you aren't up to date with this. Because from here, we go into chapter 4, then we get into something, and I want to give you a preview of this, called the confidence interval. Now, this is interesting. Have you all seen polls, and they said, like, somebody's ahead by 20 points in the polls and all this crap, right? So they can't poll the entire population. What they get is what's called a sample size. It's supposed to be reflective of everybody. Normally, it's skewed horribly. I mean, do you do polls, anybody in here? If I ever get a call to it, I'd block that call. Mainly because, first, they're using my time to get information that they're getting paid to get. So unless it's something, for like a nonprofit organization or something like that, like if they're trying to determine something about, I don't know, health or, wildfire, I'll do those. But I don't generally do them. They take a lot of time. So I've got a robocall blocker, and I just block any other number that gets through. But what happens is, nowadays, that the only way they can effectively get a poll, they have these robocalls calling, and the only people at home that'll talk to them are basically people that are either out of work or, so it's extremely skewed. And whenever you see stuff that says, it's horrible. What we're doing in chapter 4, we'll talk about how to get a legitimate sample size, and then the confidence you can have on the results, more or less the probability density function for what's going to happen. That is actually very important, and here's why. Most of you people are going to end up working in technology, actually at the cutting edge, a lot of you, because you're young. You're going to be working at creating products for the market. And one of the biggest things that they have to do is, it's called compliance, and they also have to figure out yield and how effective they are at creating products that are going to actually get out in the field. So they have to sample, and I'll just use the example of VLSI. You all know a very large scale integration or silicon chips that they make, and they make billions of these things. So they have to sample a small subset of that. My wife was involved in this at Intel. And then they have to go ahead and create software packages that will test them to see if they are effectively working. They can't test everything. There's too many, but they have to find a sample. Then if they find like 8% fail, what does that mean in terms of the total yield? And they have to find that. And there's quite a bit of information that you can glean from a fairly small sample size if it is truly reflective of the large sample. That's the biggest problem. Okay, now back to this problem. I just want to finish up 3-5.3, and I want to do this from the start, but I want to make sure everybody pays attention to this. Now, this, in my opinion, is a tricky problem, but they get a lot trickier, and so just watch this. So before, they said we have two random variables, and I'm going to use theta, and I'll use phi, and these have probability density functions. Let me get a different marker that are constant, and what this is say theta, and this is f of theta. This is going to be 2 pi, and it's 1 over 2 pi in height. It's randomly it's got a constant value and uniformly distributed from 0 to 2 pi, and it's the same thing here versus psi. I don't know if that's the variable he chose, but it's the one I'm choosing. And this has a value of 1 over 2 pi. And right here, you're going to have f of psi. So I'm showing you this. Then he says, based on that, we're creating two new random variables. When I saw this problem the first time, I thought that they were going to use derivatives to determine things. You can do it with derivatives, all right? But he chose not to. So here, it's going to be just cosine of, and it's 100t, but I'm going to use omega t plus theta, and y of t is going to be cosine of omega t plus psi. Now, omega in the book is 100. It has no bearing on the results. No bearing on the results. Then he creates a new variable, z of t, and that's equal to x of t plus y of t. Now, the real trick at this point, the next step is going to be trig. It basically boils down to, we're going to have to find out a relationship. Now, z of t is going to be given as a cosine of omega t plus, and I'm using this symbol. He uses a different symbol, but I'm using that symbol, okay? If you take a look at this, just back off, and if you're asked to find the probability density function, f of z, do you remember what I did? Anybody? Oh, actually, what they wanted to do is find a, right? They wanted to find a first, right? So how do you get a? What I did, I mean, there's probably other ways, is what I did is break it down to real and imaginary parts on a complex plane, and then I simply derived an equation that equated all the horizontal components and all the vertical components. I squared them. I got the x squared plus the total x squared plus the total y squared, and equated it to the actual hypotenuse. Do you all remember that? I'm going to do it quickly. But please just watch me on this one and don't freak out, because this is, if you look at the trig identities, you'll get lost. At least I think you're not going to find a couple trig identities that will make this happen. It's a lot tougher than you think. So if this is the real axis, and this is the imaginary axis, or j-axis, I know that anytime I have a cosine of anything, when I have a cosine of any function at all, say cosine x, that's just the real part of e to the jx. Do you all follow me on this? I'm just trying to make sure. So I'm going to go ahead and I'm going to take the first two components right here, this and this, but I know omega is not going to have any bearing on this. You can use omega, and the only thing it's going to do is skew everything by a certain angle. Everything will be skewed. It has no bearing. So let omega t equals 0. Now I plot this first one in terms of this. I'm going to keep that in mind, but it's really going to be it's going to be simply magnitude of 1, and here the angle is going to be theta. Then there's a second one, and here this angle is going to be psi, and this has a magnitude of 1. And then that has to be equated to this. Now that has a magnitude of a, so here's a. This angle right here is going to be what I'm calling, what's the name of this Greek symbol? I always put gamma here, but what?
Is it gamma?
No. I mean, actually, it might be gamma. Doesn't matter. It probably is gamma. And this has a length of a, right? Now here's what I do. Do you remember what I did at this point? I take the components in the horizontal direction, right? And I take the components in the vertical direction, and then I square them and set it equal on both sides of the equation. So if I take a look at this for the horizontal components, I get cosine of theta plus cosine of phi, and this would be equal to, now again, I'm just taking component here, and then it has to be equal to A times the cosine of gamma. And then I do sine, now these are the horizontal components, sine of theta plus sine of psi equals A sine of gamma. And that's the part I did. Do y'all remember that? Next. What did I do next? Do you remember? Yeah, what I'm going to do is say, I know that if I take this horizontal component and square it, and this horizontal component and square it, and add them together, it equals this squared plus this squared. That's my point, right? So I'll start with the A squared, and then it's going to be cosine squared of gamma plus sine squared of gamma are equal to all those squared. And I'm going to go ahead and do it this way. So I have cosine of theta plus cosine of psi, and this is squared, and it's plus sine of theta plus sine of psi, and that's squared as well. And I think everybody agrees with that, right? Yeah.
I just checked it as gamma.
Okay, good. Gamma. All right, y'all with me, class? Yeah, that's right. Delta is this. But are you all with me on this, class? So if we're down to here, now this has got to be 1, right? Because it's the same angular function. So now I get a squared here equal to, and over here, I just want you to watch this one more time. Take a look at this. When I square out these terms, I'm going to get a cosine of theta squared plus a cosine of psi squared plus 2 times cosine of the middle ones. Do you all agree with that? So I'm going to get cosine squared of theta plus cosine squared of psi plus 2 times cosine of psi times cosine of theta. The order makes no difference. Then I get plus, and then same deal here. I'm going to get sine squared of theta plus sine squared of psi plus 2 times sine of theta sine of phi. And I'm just stating the obvious. Agreed, everyone? Now, I'm just going to leave it here once you write it down. But again, I'm just doing the squaring operation and carrying it out. Only thing I'm going to do is now circle things when added together equal 1 by definition. So I know that this is going to be 1. Cosine squared plus sine squared of theta, right? Agreed, class? The next one that's going to be 1 is right here. You all agree with that? Now we have 2. The next term right here, we get from this identity, or we can group. I'm going to move these out of here. So if I have cosine squared of phi, that's 1/2 plus, and it's going to be 1/2 cosine of 2 phi. Do y'all remember that? Kind of, sort of. Just try it, see if it works. If you ever worry about these things, you try it at a couple values. Say it's 0. Cosine of 0 is 1. 1/2 plus, this is still cosine of 0, is 1/2. So it's 1 is working. Next one, say 45 degrees. Cosine of 45 degrees is what? 1 over square root of 2, right? Square that, you get 1/2. Over here, you get 1/2 plus Cosine of 90, what's the cosine of 90 or cosine of pi over 2? 0, right? 1/2 equal 1/2. That's good enough for me. It works. So what that means is these two terms that are remaining. Now take a look at this. I have twice those two terms. You all see it? What is that going to be? Well, the cosine, and this is oh, sorry, I did the wrong one. My bad. So if you have cosine of really A minus B, that's cosine of A, cosine of B. And because it's a minus, it would be plus sine of A, sine of B. Do y'all remember that one? At least this is an expansion. If this was a plus, this would be a minus. So here I can see, I'm sorry, I got ahead of myself on this one. These two terms really, if you look at that, I have 2 times that, so I have 2 times cosine of A minus B. A in this case is theta or psi. You all with me, class? So I can say all this stuff boils down to 1 plus 1 is 2 plus 2, and it's going to be cosine of, and I'm going to use psi minus theta. Now that's what that equals. Agreed, class? Now I'm going to do this. I'm going to factor this. And I'm going to say this is equal to 4 times 1/2 plus 1/2 cosine of psi minus theta. You'll understand why in a second. And I go back to here. And if you look at that, the psi minus theta right there would be equivalent to 2 phi here. Can you all see this? That means when I look at the argument that would go in this cosine squared right here, it's going to be equal to simply psi minus theta over 2. Y'all with me? Now again, the 1/2, I made sure to put the 1/2 there. So this is simply going to be equal to cosine squared of, and this is going to be psi minus theta over 2. Now, that's equal to a squared, right? So this is equal to a squared. And that means a is the square root of that. Square root of 4 is 2 cosine of, and now we get psi minus theta over 2. I hope this clears up anything I did wrong. Y'all with me? So that's how he comes up with this little trick. Now, after that, we have to go and get, that's the value of A. And he asked for the probability of A being greater than, or 1 or something like that. But here's the deal now. In order to do this, remember, this is a function of random variables, right? So we're going to get, it's actually, this is what A is, right? These two are random variables. Rather than finding an actual, well, he actually does it this way. Technically, he should do this using a derivative method, but he's not going to, so we're going to do it this way. I'm trying to follow along in the solution of the book as much as I can, but I'm spending a lot more time explaining how he got certain values in the book. So next, he creates a random variable, beta, and that's equal to, his book doesn't have the divide by 2. Psi plus, it's psi over 2 minus theta over 2 as such. And then what he does is, now try to follow me on this one. He has these two values. Do you remember when you had z was equal to y minus x? If you wanted f of z, you could say y plus x. If you wanted f of z, it would be f, and I'll call this y of z, convolved with fx of z. Do you all remember that? It's really a convolution of two functions. And you got that by going ahead and defining the integration first. Y'all remember that with those density functions? And then you put the limit, the upper limit would shift here. If it was the x integration first, then x would go to z minus y. And then when you did that with the f of y integration, it became a convolution. Do y'all remember? Now what he does, and this is kind of clever, if we had z is equal to y minus x, then what you can actually do is say if this were the case, you could say f z of z is really equal to fy of z convolved with fx of minus z. And what he's doing here is accounting for the minus sign and the argument. Do you all follow me on this, class? It's a little tricky, but you can do this. What this does is it eliminates some of the remember how when we did, I messed up that convolution thing where I assumed you could do either one first. Do y'all remember that? And it wasn't a convolution, it was actually correlation. You can't do that. You can't do that with a correlation thing. But you can do it this way, and this will work. It's a bit of a trick. So here's what he does. He says to get f of b right here, he's really just going to convolve f of, and this would be beta over 2 of psi convolved with, and then it's going to be f of minus beta over 2 of theta. In other words, he's doing the same thing I'm showing you there, only he's putting a minus argument there and you got beta over 2. Do you all follow me on this kind of? All right, so isn't this how he does it in the book? You got the solutions right there. The solutions, Matt. I'm going to spend more time. If you wanted to, you could do something. It'll work out the same way, but I spent some time with this. It's a little tricky. Let me erase this and show you something. Let me go back to the definition, and then I'm going to spend more time on that in a second. Remember how, in general, f of z, if you had, say, z was equal to y minus x. I'm just doing it with the minus sign because this, if it's y plus x, it's simply two convolutions. You all with me? Try and make it clear. So here, you would have an integral technically from minus infinity to infinity. And I'm going to do the x integral first. So x would be equal to z plus y. And then you would have an integration here from, you're going to have an integration from minus infinity to x equals z plus y. And this would be f of x, right, of x. And then over here, you're going to have f of y, and this is dx dy. And this is actually not f of z. This is the probability of z being capital Z being less than some small z. Technically, this should be a small z here. Y'all with me? Then you take a derivative of this with respect to z. Now, I don't want to go too far down this road, but you all follow. If you're really curious how you get this stuff, start by the fundamental definition, then take a derivative of that with respect to z, because that will give you f of z, right? This is the cumulative probability. Now, if you take a derivative of that, you get f of z. And I'm just going to copy this. So this, only place it exists is here, so it becomes the integral of fy of y, and then it's going to be times fx of z plus y dy, and this goes from minus infinity to infinity, but really the limits will have to deal with the functional form of f of y and f of z. You all with me? Now, typically, there was a minus sign there if this was a plus, so it's perfect convolution, right? Can you all follow me on this? But now if you make the argument here, if you take this and, this whole thing, if you make that the functional form f of theta in the argument minus, let's see, it becomes minus z minus y. Try to understand this. This is still a functional form of z right there. Do y'all follow me? Now you have the functional form that looks like convolution. It's f of y times f of x, but instead of the normal way to write z right here, I mean, I'm going to put minus z for a reason, because then the results of this convolution will have a signage. This argument will be minus z. Boy, I hope I said that right. You're going to see something. Just bear with me on this one. This isn't, I'm not saying this correctly. When you do this, oh, sorry, I shouldn't have done that. Now I know what I should have done. This should be x plus y. And then I should say, if we create a new function, call it g of x that's equal to f of x of minus x. Now you can do this thing. All right, I'm creating a new function here. Then I can say, I'm going to replace f of x in there with this function. So this is going to have a minus argument. This is plus, with me? Then I put that minus argument in there, and then it will be the convolution of the stuff, but it's going to have a minus z argument. Boy, this is not.
Did you write a z in there? Is that z plus y or x plus y?
Sorry. This has got to be a z because it's a derivative, z plus y. You don't have to go through, I mean, you can go through this when you have time. Just go to the fundamental definition and do it. It does work, but it's irritating because you have to, and this is what he does. He creates this new function right here, and he replaces f of this, and it's z plus y, and it becomes minus this. But this g of x function has this form here. Instead of having a positive going from 0 to 2 pi, it goes from minus 2 pi to 0. Do y'all follow me on this, guys? I'm sorry this is not coming out the way I'd like, but, yeah.
Shouldn't it be like y equals z plus x? Like in the beginning when you say z equals y minus x, and then like x doesn't equal z plus y.
This is the fx integration, right?
No, and like the limit is z plus y, but like if you start with z equals y minus x, how do you get to x equals z plus y?
Oh, you're right. You're right. You know what? That's the problem. So x on this side would be y minus z, right?
Yeah.
My bad. You're right. This becomes y minus z. I'm so sorry. I know this works. So this is y minus z. Now, here's the reason this function works. I'm sorry, I was leading you astray. Once you do that and you go here, create this new function, now it'll flip it. Now it becomes z minus y. That is the form of convolution. You all with me? So that's what he ends up doing. And that's equivalent to saying, now I'm just going to take f of y and convolve it with f of x of z of minus z. That's the equivalent. This is a trick that's kind of nice to keep in the back of your head. Go through this one and just review it, because if you have functional forms where instead of the obvious convolution, if it's plus, if it's a minus, then it's correlation. But if you create that odd function over there, the new function where, now this one, I'm sorry, over here where f of x is going to be equal to g of minus x, then it works perfectly. And that's what he ends up doing. So anyway, here's what he's going to end up doing. The halves there really come from the fact that beta is equal to these 2 over 2. So that beta is going to be the formal argument. You all with me, class? Back over here, now he convolves them. So you have 2 functions, and normally they go from 0 to 2 pi, but now the 2 functions look like this. Because it's beta over 2, when you take f of psi of beta over 2, it looks like this, and has a height of 1 over pi. And when you take f of fy of minus beta over 2, it looks like this. And this becomes pi, minus pi, and it has a height of 1 over pi. Y'all with me on this one? And this is going to be versus it's really versus beta over 2 versus beta over 2. Can you all follow me on what I'm trying to show you here? And this is in the solutions. Now when we convolve those two, right? When you convolve them, they're going to start at minus pi and they're going to go to pi. All right? If you convolve, you flip and shift, it's going to start at minus pi and it's going to go to pi. Are you with me? You can do this. I've done it. When you flip, you got to shift it down. When it shifts, it starts at minus pi and then it's going to finish at pi. Whenever you have these two blocks like this going through each other, you end up getting this. This is going to be minus pi to pi, and it'll look like this. And the height here is going to be 1 over pi, and this would be f beta of beta. Do you see that in the solutions, by the way? He should have something akin to this.
It looks exactly like that.
I want to tell you, this is not, take some time to go through this. There's a lot of subtleties in this one, and he flies through it. He doesn't show you a lot of the tricks. He doesn't show you anything about that convolution. Like, yeah.
Is the top one an Fy beta? Or
This is f psi. Remember, these are really what? This is psi and theta, right? Those are the density functions that he gave us. I'm using psi. I don't know if it's simple psi, but I think it is. It's psi and theta, right? Okay, you come down to this, and here's the real deal now. He wants the probability that A, I think, is greater than 1. Tell me if that's right.
That's right.
So he asks that. Now, what is A? I'll put it over here. A was equal to 2 times cosine of psi minus theta over 2, right? Or it was 2 times cosine of beta, and that was A. Now remember, I made beta equal to, I think I erased it. Beta was equal to this right here. So this is beta or B. It doesn't matter. Y'all with me? Now, it exists from minus pi to pi. So I'm going to just plot it under here so you guys can see this. So here, if I plot versus beta, cosine of, and actually when I do this, I'm going to divide A by 2. And that's equal to cosine of beta, right? Just remember that. I come over here and I plot cosine. I'm just going to plot cosine of beta here. Well, it starts at 1. And it's a symmetric function, right? Thank God he chose this one. You all with me? Now, the only place it's going to be positive, you think about this. If A is 1, 1/2 equals cosine of beta, we want the cosine to be equal to or greater than 1/2. Do you all follow me? Well, cosine of what angle gives 1/2? That's 60 degrees or pi over 2, isn't it? So if you look at this, this is pi. I really exaggerated it. I mean, this should be pi, and this should be minus pi. So pi over 3, minus pi over 3 here, and this is plus pi over 3 here. So what we need is the probability that it's inside there. Do you all follow me? And actually, I'm showing you, it's actually the area here. So it's minus pi over 3 to pi over 3. We need this area. Can you all follow me, class, on this one? That's really going to be the probability that A is greater than 1/2. How many see this right here? Spent a lot of time on this one. I'm sorry I'm spending. Are you with me? It's really coming down to using this as the break point, the limit, because he states he wants A equal to or greater than 1, which means 1/2 cosine beta is the threshold, and then beta has to be such that, or B has to be such that the cosine will be equal to or more than that. And this is the range where it would be. Now, how do I get this area in purple right here? Anyone? I mean, you can do it so many. And how would you guys get it? It's a triangle, right? It's a right triangle. How about we take 1 minus twice the area in this little guy? Agreed, everyone? So what is that going to be? 1 minus, what's the area here? Well, this right here would be what? If pi, this is 1 over pi. If we went, this is going to be 2/3 pi, correct? From pi over 3 to pi is 2/3 pi. So what's the height here going to be? It's going to be what? That times 2/3, isn't it? 1 over pi. So if you think about it, it's 1 minus, then you can say it's twice the quantity of this area. What's this area? Well, this is, I hope I'm drawing this right. If you look at this, this is pi, this is 1 over pi, right? If I come out to pi over 3, the height of this right here is going to be 2/3 of 1 over pi right here. Can you follow me on this? So this is 2 times, and this is going to be 2/3 pi, and then this pi and that pi cancel, so it's minus 2/3 squared. Is that right? Oh, no, the 2 goes away because this would, if I took this right here, this times this, I'm going to get 2/3. I'd multiply it by 2. So it's really 1 minus that is 1 minus 4 over 9 is 5/9. And I think that's the answer he has. But again, it's just taking, I'm not going to calculate the area in those odd regions between them. I'm calculating 1 minus twice the area in that upper triangle, the last part there. Can you all follow me on this, guys? Is that right, by the way?
Yeah.
All right, next he asked for what? You guys help me on this one. Remember, this is the probability density function right here that'll work.
The probability that A is less than or equal to 1/2.
All right, how do we get that? Go back to this. I need your help on this one. So if A is 1/2, right? If I put 1/2 equal to 2 cosine of beta, and I want beta, so it's going to be 1/4 equals cosine of beta. It's less than?
Yes, sir. Less than or equal
All right, what is beta that gets that? Give me the angle, and give it to me in degrees, not radians. I don't know myself. You can give it to me in degrees and radians. I just need the inverse cosine of 0.25, which I don't remember.
It's 1.3 radians.
Boy, I wish that was in terms of pi. But how many degrees?
Trying to figure it out.
75.5.
Okay. Okay, now, just go with me on this one. Ready? I want to make sure I got everybody's attention. Now, here's the density function right here, right? Actually, let me blow it up and put it here. So when we look at this probability density function for f beta of beta, it looks like this. This is 1 over pi. This is beta. This is pi. This is minus pi. And down here, I'll try to draw the cosine business again. This is cosine of beta. Can you all follow me right here? Now he gives us he tells us where the cutoff point, 75.5 degrees. That's plus or minus. You all follow me? It's on both sides because it's a symmetric function. So if you come up here, I know that's 90, so 75.5 degrees is here, minus 75.5 degrees is here. You with me? We want the probability that's out in that area, right? Less than, and you can see the cosine is less than. So come up here, find minus 75.5 degrees, plus 75.5 degrees, and what we need is this area, right? How are you going to get that area? Anybody? This is something on quizzes or exams, people will get a little confused. How would you get it?
Would you integrate over the whole area and subtract
Well, we want this area and this area, right? How about we say it's twice this area? You give me that? So it's 2 times this area. What is that area going to be? Now, think about this. This is a right triangle, right? Constant slope. You could take this and turn it in terms of pi, right? So how would you do that? I mean, in terms of radians. So you could say 75.5 degrees, right? And you said it's how many radians, right?
Yeah, 1.3.
So if you multiplied, I mean, think about that. If we take pi right here and we multiply it by something, we're going to get, is it 1.5, did you say?
1.32.
Now, if we divide that by pi, we would get alpha, wouldn't we? I mean, you don't have to do it this way. Anybody got any take on how you get this area? This is what? This right here is 180 degrees, right? Correct, class? And this is 75.5. How would you do it? Remember how I did it last time? I had a pi over 3 there, right? And I said this total width was, tell you what, why don't we do it this way? I think you'll get me on this one. How do you get the height? Well, if it was a full pi wide, it would be 1 over pi, right? So if it's this wide, it's whatever this distance is in radians times whatever that fraction is, right? Times this. I'm trying to, can you all, I'm not saying this very well. Let me do it over here. I know you guys probably see how to do it, but my mumbling isn't helping. Let me try it. We'll do it the old-fashioned way. Why don't we do it this way? So all this is in radians, right? So here's what I'm going to do. I'm going to make a simple triangle like this. And here's what I want, is this area, right? This is 1 over pi. This would be pi. This is the same exact dimensions right here. And I know this point in radians is 1.32, right? 1.32 radians. All this stuff is in radians, correct? And actually, hold on. I flipped that, so what you need to do is take pi and subtract that to give me this break point right here. Because I'm starting at this point backwards. So this distance from here to here would be pi minus 1.32. I don't know what that is, but you all follow me on this, class? I need the width.
1.8.
All right, so this is 1.82 radians. Now, I need twice that area, right? Well, this area, if I can find this height, I can just take width times height, and I should be able to get it, right? Because we'd have to multiply by half if it's a triangle, but we're going to multiply by 2 because it occurs on both sides. So how do I get this height? Well, if I look at this right here, if you think about this, the rise over run. Rise is 1 over pi. The run is pi, right? So that's 1 over pi squared, right? Isn't it, class? So that means 1 over pi squared times that would be the height. Do you agree with that? So if we take this, if we take 1.82, and then we take that, which is 1.82, divided by pi squared right there, that should be twice this area. Do you all agree with that? In other words, I'm taking width times height. Instead of dividing by 2, I'm leaving it alone because on the other side, we're going to have to add that one. What does this come out to? I don't know. I can't do this in my head. I hope that's right. I believe it is. But I can't do it in my head.
0.335.
What is he getting his answers?
It's 0.25, 0.2435.
All right, what did I mess up? It should be twice that area. That is 1.82 pi minus 1.32? 1.82 squared over pi squared. Give me that again. They might be wrong in a book. Can you see what his calculation's based on or not?
It says the probability of beta greater than 1.3812.
3.8. Wait a second. What did we get for this one? 1.38? You had 1.32.
The arc cosine of 0.25 is 1.318, so I just rounded 1.3.
What did he say? Greater than?
It says 1.38.
That he's wrong. You're right. He made a mistake.
Yeah.
But that's how you do that problem. Is there another part? I don't think there is. All right. I want to do. What's the next problem on this one? And then I'm going to get to the next section. What?
Explain again real quick, like when it's a probability A is less than or equal to 1/2, why there is it all of that up there?
All right. It has to do with the cosine. If you look, I plotted the cosine right below this versus beta, right? So the cosine, and because it's from minus pi to pi, cosine's an even function. It looks like this, right? So if we hit this point, remember, that's the threshold. We want to find the likelihood the cosine's less than this value. That means the likelihood the cosine's here or here, right? Then I come up here, and that's the same thing as the probability of the argument of the cosine being from here to here or here to here. So the only thing I did is take twice the probability it's here, or the area under that curve. That's all I did. You all with me on this, class? It is a little tricky, this one. The biggest problem was that crazy reverse convolution he does. That's the only real trick in this. Well, the whole, the trig identity was a little tedious to me. Okay, everybody with me?
Can we just know from now that from all that the convolution is simply a triangle?
Well, the only reason it's triangles because they're both constant dense. They're uniform densities. If they were different, it wouldn't be. Yeah.
You want us to memorize those trigonometry things, like the formulas we're given?
No. You should know Euler's.
Yeah.
All right, that's it. Go ahead.
Is this a good question?
Please be helpful because
I'm not going to ask you this problem. But if I give you something where you get something crazy like the sine and cosine business, or x equals sine, y equals cosine, right? And I won't put the 100 at t if I put theta and phi. And I asked you, say z was plus, not minus, plus x plus y. Hear me? How would you get the density function for z? That one's kind of, it falls in your lap. Do you all follow me on this? And from that, the probability of cosine is between like 0.1 and 0.5 or something, 0 and 2. I mean 0 and, no, between say, 0 and a half, something. In other words, I'm not going to give you something that's really going to screw with you in terms of reversing the convolution integral. All right, but know at least how to do that part.
So you've seen a problem like
Huh?
that? So you've seen a problem like that before?
Yeah, we have, actually. And how did he do it with the derivative? If you remember, he took a derivative. See, if you take derivatives to get the density functions, do you remember how we did it before? He found the density function by taking a derivative of another, and then he looked at that, and he said, well, it has to be double because the cosine actually had negative and it's an even function. You would have a symmetric type of area under there. But I'm really getting off topic. But yes, you did have one like that. But it didn't have two variables. All right, two independent variables. All right, let me go ahead. Next problem. Hold on, let me erase this to catch my breath. I'm sorry I didn't explain this better. The trig is a pain, and then that convolution is a pain. But, all right, go ahead.
This is a big problem.
What?
3-5.4.
What does this say?
Many communication systems connecting computers.
I'll tell you what, skip that one, it'll take too long. This is just going to have a probability. Here's the whole deal with that one. The density function is going to be exponential. It'll be 1 over some constant t, exp to the minus t over cap t u of t. Now he gives you that, and then he's going to give you a constant density function. I'm just going to tell you, at the end of the day when you do it, you're going to find a variable z is equal to y plus this t variable, the delay, and you get regular convolution for that one. It's not hard. If we have time, we'll do it. Next one.
This 3-5.5. Two statistically independent random variables.
Oh, yeah, this is a good one. Pay attention. This is 3-5.6, right?
2-5.5.
5. And this has f of x equal to, what is it?
5 exponential negative 5x times the step function.
Times u of x. And then f of y is 2, is that right?
2, yeah.
Either minus 2x or 2y, u of y.
And those are probability density functions, of course.
Yeah, these
And
are
then
probability density functions. And go ahead.
For the random variable z equals x plus y,
This is a godsend.
for part A, find the f sub z of 0.
Now, I'm going to show you something. Remember, the way we could do this is what? F of z would be simply fx of z convolved with fy of z. You all follow me in that? It's an x plus y here. We could convolve those two functions, right? Now we can do that, and basically you got to leave one alone, you got to take the other, you flip it and shift it through there. But here's the characteristic function coming to the rescue. Please listen to me. This is in section 3.7. Instead of using their definition of characteristics function, we're going to make use of our knowledge of Laplace transforms. And now I take a second and mention this. When you had Laplace transforms, if you had f of t, it would transform to f of s. I thought about doing it with Fourier. Laplace is easier. Okay, do you remember this? And in general, f of s is equal to the integral from 0 to infinity of f of t, right? And we can do it with Laplace or Fourier, but I'm going to use Laplace for this one, times, and then it's going to be e to the minus st dt. That's Laplace. By the way, since I'm at it, Fourier transforms are just the integral from minus infinity to infinity of f of t, and then it's going to be times e to the minus j omega t dt. The only difference between the two is here s is equal to j omega plus sigma. Sigma is really something has to do with stability did you have your controls classes or not? You'll find this out. It has to do with stability or region of convergence. I think you had that, right? In signals and systems, the ROC, region of convergence. But they're identical, and the only really big exception is the lower limit here goes to minus infinity. That starts at 0. It's a single-sided Laplace. Yeah.
Sorry, S is equal to j omega t what?
Plus sigma. Do you remember? S was j omega plus sigma, and sigma had to do with the region of convergence. How many remember that? Don't worry if you don't see everything about this, but that's region of convergence is something you're going to see over and over again when you get into controls in your higher level classes. So, but Laplace are much easier in general. So, what I'm going to do is this. I know if I have two functions convolved, and the argument here could be t. Doesn't matter if it's z, t, anything. Y'all with me? You can take the Laplace transform of both, multiply them together, right? And then do a partial fraction expansion. Find the individual functions that you know the inverse transform or the transform pairs. And I'm going to start this over here by saying, I know that e to the minus at u of t goes to 1 over s plus a. Now, I hope you all remember that. How many do? Everybody should. This is something that's kind of universal. You have to know this. And if it was Fourier transform, it would be 1 over what? A plus j omega. Follow me? S would be replaced by j omega. There's nothing tricky here. So now, when I do this, I want to do this using Laplace transform theory. I'm going to carve this problem into something that you would recognize, and I'm going to just say that I'm going to let z become t for now. We'll put it back to z, but just so you keep your head on straight. My z's look like s's sometimes. So now I'm going to say my f of t that I want is really fx of t convolved with fy of t. Just pay attention. You'll be thankful you did. Now, instead of doing the convolution, everybody say amen. We're going to just do Laplace transforms and multiply them because it's a pain to do these convolutions. I flipped and shifted these things till my eyes were crossed. All right. So what is going to be fx of t's transform? Take a look. And then take a look here. What?
5 over s plus 9.
You all see it? Right? How many see that right here? Let me do it over here. So this becomes 5 over s plus 5. What about this one?
2 over
Remember, it becomes, that y becomes t. Go ahead.
2 over s plus 2.
Excellent. Can you all follow me? You're not used to thinking of Laplace transforms with anything but time in one domain. It doesn't matter. It can be x, can be z, it can be anything. The other domain, the S domain, is where it gets transformed in. It doesn't have to have a direct physical interpretation. All right, this is just the transform pair theory. All right, now what do you do with that? Do you remember the next step if you had something like that? Those are two poles, right? You agree? How many see this? All right, so the two poles, we assume one is a over s plus 5 plus b over s plus 2, right? So how do I get a? Y'all remember?
You multiply by s plus 5 and then do the limit from negative.
Just say it equal to minus 5.
Or
Here's the deal with this one. If you take a look at this, right? Multiply everything but s plus 5. S plus 5 goes away here, right? S plus 5 goes away here. S plus 5 becomes the coefficient of b. Then let s go to minus 5. This term goes away, doesn't it? And over here, when s is equal to minus 5, because we're trying to find a, right? What do you find? I got 10 over 2 minus 5 is minus 3, right? Minus 10 thirds. How many see that? Can you all follow me on this? So this is minus 10 thirds right here. And what's the next part? S plus 2, right? So what do? They call it the cover-up method. Come over here, use your hand to cover up the s plus 2 because we multiplied everything by it. Then let s go to minus 2, correct? At minus 2, what do you get? You get 10, right, over 10 thirds, right. And by the way, these always break down. When you have anything like this where you have two single poles multiplied by the other, there's no s on top, it'll always, one coefficient will be negative of the other, always, okay, always. Now, take a look at this, and now we want to get our f of t again, or our f, what did I call it? Yeah, I'll call it fz of t, which is really going to be fz of z in a second. So what is it? Well, what's the inverse transform of that? Come on, guys.
it'll be negative
Minus
10
10
over
thirds
3.
is the coefficient, right?
e to the negative
Times what?
e to the negative 5t.
Yeah, now you, that's what I wanted to get. Minus 5, and instead of t, I'll put z in right away. Z, and it's going to be, the other one is plus 10 thirds e to the minus 2z, and this is all times u of z. Do you all see that? Take a good look. Isn't that easier than doing the crazy convolution, flipping, shipping?
This is what you should quiz us on.
Please.
Well, thank you for telling me my job. My wife does that all the time. Take out the trash.
I'm sorry.
No, don't worry about it. I understand. This is something you appreciate because you've had it before. Now you see a reason for it. Go ahead.
But if the quiz on it, could you possibly?
Oh, brother. Give it up, buddy. You're not a DA. All right, stop it.
I'm gonna ask if you could provide the
Laplace transform
chart.
tables.
Right.
Yeah, I'd figure out of the kindness of my heart to give you information that you may have
We always
forgotten.
had the tables back in signals on the test.
I never gave table. Anybody ever have me for signals and systems? Never gave tables. What kind of a person would do that? Somebody's trying to destroy your educational career. Okay. Y'all agree with that? Now, before we go on, I don't know why I'm so happy today. Got a good night's sleep, I guess. What's the next thing they ask?
He wants f of z of 0.
What is f of z of 0? Take a look at this. Here's people's make mistakes. Here, listen, take a look at that. Let z be 0. What do you get? 0. Is that the right answer? Hallelujah. Next one.
The value for which f sub z of z is greater than 1.
So, that one's tricky. They want f of z greater than 1, right? So you set it equal to 1, right? Help me out on this one, guys. So if I set this equal to 1, I'm not out of time for once. All right, so if I set this equal to 1, how are you going to solve it?
Natural logs.
How are you going to do it? You can, all right, take a natural log of everything, right? You know the natural log of what? A times b is log of a plus log of b, right? But what about this? Is it? I think you need a root solver for this one. All right, you can go ahead and multiply both sides by 10/3, or by 3/10. So you get 3/10 over here. Now what you have is this push-pull relationship, and you have e to the minus 2z minus e to the minus 5z equal to 3/10, right? Now remember, taking a log, you could take this one to the other side. If you take a log, you can go ahead and get this simply minus 2z, or basically you get minus 2z here, but when you take this to the other side, you get a complicated thing. Do you all see what I'm talking about? There is no simple way to get it. You need a root solver. Does anybody have one of those things? You can plot it, take a derivative. If you think about this, if you create a function and you put this equal to 3/10 plus 5z, take a derivative with respect to z on both sides and set it equal to 0, because this is the solution at that point, you can do it. But what do you get for this? It would take a root solver for this one. You can iterate too.
It says he gets 0.45.
Can anybody confirm that? Because he does not say the method he uses, but I believe, you can do this with a slide rule, I believe, kind of cleverly, but I think it takes a root solver.
You can take natural log on both sides.
Go ahead, and what happens? Remember, this is log of a plus b, right?
Yeah.
Log of ab is this. Natural log of a plus b, you can't break out like that,
Yeah. Oh.
right? So you can't. What did you get?
The solution is the x value of the point of intersection. I don't know what that was. They gave me 2.
What is that?
They gave me 2 x values.
2 z value.
Or 2 z values, correct?
Well, one of them's positive, one of them's negative, probably.
I got 2z values.
It's just, yeah, 0.195 and 0.454.
So maybe we do have 2. All right, so does C have 2 or just 1? We got one of them, right?
He has 1.
And you got what? 0.1?
0.195 and 0.45.
Yeah, and I'll tell you something about this. This is a classic function. I'm used to these things because long ago I did lightning research. And lightning's current has this response. So normally if you have something, and I'll just show you for lightning, I of t was equal to typically some constant I naught, and there'll be e to the minus t over tau 1 minus e to the minus t over tau 2. This is a classic thing. Here tau 2 is much, much greater than tau 1. And it'll have this kind of double exponential curve. This is I of t. Versus t, it'll do this. All right, it just does it. So there will be 2 values where you have a relative, like if you have anything below the peak, you'll have 2 values that attain that point. So you're right, your root solver should have 2, but he's got only one of them. Both would be right. You all with me?
Wait, here's the match you over here.
0.454.
That's
Okay,
the first
that's
root.
the second one.
That's the first root. The second root's the next one. And that's absolutely true. Here, it's a double exponential type of deal. Okay, I'm not going to give you a root solver. I would expect you to be able to solve a quadratic. Y'all hear me on that one? But nothing where it's going to be complicated roots. All right. What's the next problem? And then I'm going to, actually, y'all appreciate that Laplace transform crap? I want to show you something with a moment too. And I want to do a problem in the next section. So let's look at section 3-7.1, the problem there. I want to do this.
Are we skipping part C though?
Well, let's see.
It was the probability that Z is greater than 0.1.
How would you do that, guys? Listen, if this right here, where's my f of z? I erased it. If you had the f of z that I had here, remember it's just a couple of exponentials. F of z was equal to what? 10/3, and it was e to the minus 2z minus e to the minus 5z, I believe, right? U of z. So how do you get the probability that z is greater than what?
0.1.
0.1. Anybody?
You set it equal to 0.1?
No, probability. This is f. That's a density function. How do you always get probability if you got density? Integrate what? Integrate 10/3, the density function, e to the minus 2z minus e to the minus 5z, right? And then you go from here, it's 0.1 to infinity, right? Can you all follow me? How many see that would be the right? Is that the way he does it, Zach?
Yeah, he does it.
It's going to be that easy, all right? I want to kind of move on with me. Let me do that problem I just mentioned, problem 3-7.1. By the way, these are great problems, but now you're going to see another benefit of this for calculating the actual first and second moments. I'm going to do it. Before you read that problem, let me just set the stage for this.
In the text or in the back of the?
In the problems, in the back. All right, so first, and I'm going to do it with, I could do it with Laplace. I want to do it with Fourier this time. If you have f of t, and it goes to f of omega is equal to the integral from minus infinity to infinity of f of t e to the minus j omega t dt. That is the definition, right? Sorry for moving so quick. Now, if I take a look at this, and if I wanted to know something about, please listen this time. If I go ahead and I take a derivative of f of omega with respect to, and I'm going to do it with respect to omega, now what I get is the integral, and here, because it's with respect to omega, I get minus jt right here times f of t e to the minus j omega t dt from minus infinity to infinity. Only thing I did is take a derivative with respect to omega there. Y'all with me? I'm not trying to run too fast, but now, if I multiply both sides by j, and you've had this, if I multiply this by j times j is minus 1 with a minus, this goes away, and I get this, right? So, hear me now. This I've done with t. Now, typically, typically these functions are in either x, y, or z. You all with me on this? So if you take a look at this and you replace t by x, I'd say j times the derivative of f of omega with respect to omega, but now I'm replacing t with x. And now I have, it's the integral from minus infinity to infinity of x, just watch this, f of x times e to the minus j omega x dx. You all with me? Now remember, we can take a Fourier transform of darn near anything fairly easily. Most normal functions. We can take a derivative with respect to omega and we get this. And then if we do this, now that I've got x in there, if we let omega equal to 0 right here, then this goes away. Can you all see that? And what is the integral of x, f of x, where f of x is a density function dx over the range it exists? The moment, right? That is the expected value. Here's another reason you should love this stuff. It makes getting the moment trivial. And we're going to do this problem, all right, with that in mind. Everybody hear me on this? So, this is problem 3-7.1. Now, you're going to need to read through this section and section 3-5 and make sure you can do the problems, especially in 3.5. But 3.7, you're going to see this stuff's now, it's a cakewalk kind of deal. You'll see it now. All right, it makes life easier. All right, go ahead, that one.
A random variable x has a probability density function of the form f sub x of x equals e to the negative x u of x.
This is a dream.
And an independent random variable y has a probability density function of f sub y of y 3e to the negative 3y u of y. Using characteristic functions and the probability density function of z equals x plus y.
All right,
And then
pull it up. Now,
Oh, find the probability density function,
they want the probability density function of what? Z is equal to?
x plus y.
All right, how many C we're just going to have to get f of z is what they, well, actually they want f of z, I think, right? All right, to get f of z, it's simple convolution. How many see that right there? Y'all with me? Just take the two, convolve them, you got it, right? Now, we're not going to go there. But we'll go there first. We'll get f of z. So we got to convolve these. You going to do the convolution, guys? No. What are we going to do? Laplace. Now, he calls it characteristic. Don't worry about it. Laplace. We'll use Fourier to get the moments, all right? Because it's trivial at that point. All right, just watch and see. So I'm going to go ahead and I'm doing the convolution of these two in the frequency domain or the multiplication. So what's the transform of the first one? In other words, f of x times f, and really should be of z, f of y of z. Now I transform them to f of x of omega, and it's times f of y of omega. The z and x are gone. So what is this equal to, guys? Transform the first one, what do you get? Come on.
1 over s plus 1.
Right. Does everybody follow me on that?
There's supposed to be a convolution symbol between.
Oh, yeah.
between them.
Yeah. And the reason we can is this miracle right here, right? Okay, next.
3 over s plus 3.
Does everybody agree? Okay, what does that equal to? A over s plus 1 plus b over s plus 3, correct? All right, and I'm going to do it over here. Boy, this makes life a whole lot easier for a lot of reasons. But so what is that going to be? Let me just get this. F of x times f of y. What does it equal? How do you get the first coefficient, guys?
You multiply,
Cover up, s equals -1, right? So that's 3 over 2, isn't it, class? So that's 3 over 2. And it's over s plus 1. Want to take a guess at the next one? Over s plus 3, correct? All right. Now we've got the transform of it, and we got to go back to the z domain, correct?
correct.
Right. What do we get? Let's go ahead and get f of z by taking the inverse. We know there's 3 halves in both, right? I'm going to factor that out. You tell me if this is right. All right, now, what's this one go to? Thank you. E to the minus z, we'll put the u of z last. What's that one go to? Huh? Right, and then the whole thing's times u of z, right? Does he have that, Zach? Does he have a density function like that somewhere?
Yeah, he does.
All right, now what does he ask for? F of z is what? What
That
is-
was all, that was all.
What is he asking in the first part?
That was the final answer for everything. That was the first part.
What does he ask?
Um, Using characteristic functions, find the probability density function of z equals
We did
x
it,
plus
all right? We didn't use characteristic, we used Laplace. It's better for this. Next.
Oh, well, I guess you can do 3-7.2 goes with that one.
What, is that only one problem? One question? All right, what's it? 3-7.2.
Find the characteristic function of a Gaussian random variable with zero mean.
No, it can't be the same one. There's not a second part to that? All right, I'm giving you a second part. All right, for this one, I wanted to get to this. Now remember, we had those density functions, right? How do I get the moment of f of x? Remember before, you'd have to multiply this by x and integrate it, right? Let everybody say I hate integration by parts, because I do. But if you do the transform, right? Now we're going to do this. I want to do this part. By the way, I didn't give you my book, but I want to show you one thing. Because this is in here. And, well, we're going to, if you wanted to get suppose I wanted to get the expected value of x for this problem. What you would normally do is multiply this thing by x and do an integration. It's integration by parts, right? However, let's take a look at this. If f of x is equal to e to the minus x u of x, the transform of this becomes simply 1 over, and I'm going to go j omega on this one because I did the thing with j omega. It's going to be simply 1 plus j omega. Do you all follow me? I'm going to just do Fourier because I developed the argument with Fourier. I can do it with Laplace too, but this is probably easier. All right, now I know if this is my f of omega, if I take a derivative of f of omega with respect to omega and multiply by j, first it's a derivative of this with respect to omega. I want to just write it down for you, right? What that's actually equal to, and I'm going to multiply by j here, that's equal to the integral of, now it would be t times f of t, and I'll put down x in a second, e to the minus j omega t dt from minus infinity to infinity. Just let me finish my thought here. Do you all follow me? I'm trying to show you what I just showed you a second ago. How taking this derivative, I've got this, right? This is f of omega. If I take a derivative of that with respect to omega, throw a j there, that is equivalent to this, right? Now, that t there is really my x there, right? So I can say next, if I do this and I put an x in there, you don't have to do this. F of x, x, and then x. All right, and then I let omega go to 0. Now I have that moment, right? Correct? So I have to let omega go to 0. So now I take a derivative of this with respect to omega, let omega go to 0, and multiply by j, and now I have that moment. Do you all follow me? Without integration by parts. I'm going to do it right here for you. That's the one thing I wanted to get to today, and I know I owe you some time. But if I take a derivative, what is the derivative with respect to omega of what? And I'll just put it as 1 plus j omega to the minus 1. Isn't that minus 1 over 1 plus j omega squared times j? Isn't it, class? All right, multiply that by j. Gets rid of this stuff, right? Now, let omega go to 0. You get 1, don't you? Isn't that right? So when you let this, you get 1. That means the moment of that is 1. All right, the first moment. Do you all follow me? How would you get the second moment? And take a guess. First moment, 1 derivative. Second moment, 2 derivatives, right? And you might have to adjust for the j term, but that's inconsequential. And then you just put omega equals 0. You all follow me? That's really nice. It saves you integration by parts, and also for the convolution, the earlier part. That's why I like using the character, he calls the character. I like using Laplace transforms, Fourier transforms to solve these things because it's trivial. It gets rid of the partial integrations. the convolution pain in the butt. I'll give you some more problems, please do them. So the next logical question is what's in our quiz? Section 3, and maybe something that you would benefit a great deal with the Laplace transform / characteristic function, all right?
You said section 3, didn't we?
Section 3-5 and section 3-7, the beginnings of it, what I'm just showed you now, all right? Because it really will work the same type of problem, two different ways. It's much easier to do without convolution. I'll give you your tables.
Thank you. Could you possibly, at the beginning of next class, go back over this again?
Yes, I'm going to. I'm going to give you some homework. I'm going to beat these things down.
Because the Laplace, what we did, that makes sense, but the moment thing.
And I might add, if you look at the rest of the problems in section 3-5, some of them can be done this way. Actually, all of them can be done this way because they're convolutions, and it's so much easier to just do Laplace transforms, in my opinion. But of course, I'm me. Please make sure you go through this. It gets even hairier in a second, but